before I've gone through so many slides. Right. So sorry for the first few slides that are cut off. But just to give an overview, we're talking about temperature scales being converted from degrees Celsius to Kelvin. And so moving the intercept to 0 Kelvin, then we see that the volume will be 0 at 0 Kelvin. And so we define this temperature scale to be the Kelvin scale as the temperature when the volume is equal to 0. Okay. By doing so, this linear fit of the volume versus temperature will then be this convenient volume being proportional to the temperature. So that if we decrease the temperature, the volume of the gas then decreases, and when temperature is equal to 0, the volume should be equal to 0 Kelvin. And that's why the SI unit for temperature is Kelvin. But we have this conversion between Celsius to Kelvin. We can get away by dropping the 0.15 depending on the significant figures that we have in the problem, but essentially it's this addition. Right, so a little bit of practice here converting Celsius to Kelvin. Okay, water freezes at 0 degrees Celsius, and we'll learn about freezing point and boiling point as we go along the thermodynamics topics. Right, so we have there Kelvin is degrees Celsius plus 273. We'll just use the 273 scale, dropping the 0.15. Okay, so 0 degrees Celsius to Kelvin would therefore be straightforward, right? 0 degrees Celsius, simply add 273, that gives you 273 Kelvin for 0 degrees Celsius. Okay. Right here, the temperature of liquid nitrogen is given in Kelvin. How do we convert Kelvin to Celsius? If we look at the relationship between Kelvin and Celsius that we've derived in the previous slides, Celsius will be derived therefore by subtracting 273 from the Kelvin scale, right? So 63 Kelvin subtract 273 will give you a negative degrees Celsius unit. Okay. Cool. So yeah, so you sort of see the pattern here. And so we can do the same thing here for these 2 Celsius degree temperatures, 46 degrees Celsius to Kelvin. Simply add 273. Cool. And 60 degrees Celsius plus 273 to convert that into Kelvin. You have, right. So if we then look at these 2 temperatures in Celsius, 46 degrees and 60 degrees Celsius, that's a temperature difference of 14 degrees Celsius, right? 14 degrees Celsius was, of course, obtained as 60 degrees minus 46 degrees Celsius. But notice that if you also do the temperature difference in terms of Kelvin, so if you get the temperature difference in Kelvin, then this will be subtracting 2 temperatures, 333 minus 319. You will find that 333 minus 319 is equal to 14 Kelvin. Okay. So here is now an important concept where if you convert Celsius to Kelvin, you add 273. If you convert Kelvin to Celsius, you take away 273. But if you're taking the temperature difference, delta T or temperature difference, notice how the temperature difference in Kelvin is the same as the temperature difference in Celsius. Because of course, if you subtract this 2, doing the conversion and subtracting these two during the conversion process, 273 cancels each other out. Right? Okay, and so when you're doing the temperature difference, you can simply subtract the temperatures in Celsius and change that Celsius to Kelvin units without doing anything else. And you should come up with the same temperature difference. Okay. I see a common mistake where you're getting the temperature difference, you subtract the two, hence have 14 degrees Celsius, and then add 273 later on to convert that to Kelvin. Well, this solution is wrong. Okay. Because then you've converted to Kelvin twice. So keep this in mind, because as we go along, we will be doing a lot of temperature differences or changes in temperatures. And so it's important, it's really useful to remember that when you're taking temperature difference, the Kelvin scale is equal to the Celsius scale. And if not temperature difference, then you do the conversion between Celsius to Kelvin or vice versa. Right? Okay. Cool, is that okay? And we can move on. Right, now, so we've seen, so microscopically, Robert Brown observed that objects, of course, they're made up of atoms and molecules. And Robert Brown observed that microscopically, these atoms and molecules, they continuously move randomly. So this random motion, random movement of atoms and molecules, not just in gases, although they're easily observed in gases and liquids, it's also true for solids where the atoms and molecules randomly move inside of the solids. This random motion is called the Brownian motion after Robert Brown. And he observed that when the temperature of the objects increases, the movement, the motion of these atoms and molecules and ions increase, meaning when the temperature of the objects increase, the atoms moved faster. And so he said that the temperature should be proportional to the average kinetic energy of the particles, the atoms, ions, and molecules that make up the object. Right. So kinetic energy, of course, is proportional to the speed squared. We learned that kinetic energy is the energy of motion. So any object with mass that is moving, right, will have some kinetic energy. So therefore, it follows that as the temperature is proportional to the kinetic energy, then the temperature should also be proportional to the average speed of the atoms and molecules that make up the substance. Right? So if we look at this, if we look at an object microscopically and look at what's happening to the atoms that make up the objects, and say, for example, you have this piece of metal that you bring close to the flame. So this metal will acquire energy in the form of thermal energy or heat from the flame. And so this object is heated up. If you look microscopically at what's happening to the atoms in this metal strip, you will see that near the flame where it's hotter, the atoms are moving faster. And farther away from the flame where the atoms are sort of cooler, they don't have energy from the flame, the atoms are sort of moving slower compared to the atoms that have higher energy. Okay, and this is a good, animation demonstrating how the temperature is proportional to the average speed of the atoms, meaning the higher the temperature, the closer the object is to this flame, the faster the particles are moving, and therefore the more kinetic energy they have. right? So if you think about the atoms that are moving, okay, they acquire heat, they acquire thermal energy, and that causes them to move, to vibrate. So as they move and vibrate, they tend to move farther away from each other, right? And the higher their temperature is, the more they vibrate and the farther they move apart from each other, okay? Right? And so therefore it would then make sense that, okay, the faster the molecules move as a result of higher temperature, the object will then expand. Right? So microscopically, what happens to the atoms as the object heats up is that the atoms vibrate faster and faster. As they vibrate faster and faster, they move farther and farther apart from each other. That's what's happening microscopically. But macroscopically, what we observe with our eye is that the object tends to expand when they are heated as a result of the atoms moving farther and farther away from each other. It then follows that the object contracts when it's cooled because the atoms, they're cold, so they tend to huddle around each other, trying to, conserve their heat. And so when when objects are cooled, they tend to contract as atoms squeeze together. And when objects are heated, they tend to expand as atoms move farther apart from each other. And this expansion is quite dramatic, and that's why you probably notice, gaps in concrete. It's especially noticeable in bridges. If you drive over Harbor Bridge, you notice this. If you drive over it, you notice like humps due to the gaps that they put in the bridges, and these gaps accommodate the expansion of materials as materials heat up. Okay. This is a picture of what happens this is a railroad track in Adelaide, which expanded dramatically during a heat wave, and there's no room for the metal to expand, and so it got deformed like this. Okay. Right. I do this all the time. Okay. If you cannot open a jar, the lid is so tightly, it is so tight, run it over hot water. Okay, the lid will expand faster than glass, and so you can easily open the lid. And you can easily prove this the next time you're trying to open a jar, and your muscles are not strong enough to do the job. Okay. Right. So, thermal expansion is also the concept behind the thermometer. So, thermometer is a device that's used to measure the temperature of the system, and it operates by the expansion of some material. So the alcohol in glass thermometer takes advantage of this concept where the alcohol expands faster than glass. So it's similar to this concept here, and I have to make sure my hands are warm because heat, right? High temperature causes an object to expand. So as if I hold this, notice how the liquid sort of rose up because heat from my body, the liquid, and of course the glass acquired heat from my body, and that caused the liquid to expand and bubble up towards. You can also do the same thing and sort of, right. So it's a similar concept to the alcohol in glass thermometer. When the temperature increases, the alcohol is heated up and its volume expands. So as its volume expands, the level of the alcohol in the glass rises up, and you have this scale that tells you what temperature, what's the temperature according to the volume expansion of the alcohol. Right. Now the question is, what determines whether, in the alcohol and glass or this demonstration here, of course, the glass and the liquid had expanded at different rates, right? Because if they expanded at the same rate, then you won't observe anything. The liquid would still stay the same here because there's no change in volume. But what determines, you know, why one object expands faster than another object? This property of the object is called the coefficient of expansion. Okay. So the coefficient of expansion is a property of the material that determines how much the material expands. So if, yeah, and we'll talk about these two coefficients of expansions, alpha and beta. But first, let's consider this rod. So this rod, it's initially at temperature T0. So this is the initial temperature, or Ti, meaning Ti is equal to T0. Initial temperature is T0. Okay. If you heat up this rod, then this rod will expand because as we've learned, the atoms vibrate and they move farther apart. And so you have this expansion delta L. So delta L is expansion of the rod because of the increase in temperature delta T. It then makes sense that the expansion, how much the rod expands, this expansion will be proportional to the temperature, the change in temperature. Because if you heat up the object by 5 degrees Celsius, for example, the object expands by this much. If you heat it up by 10 degrees Celsius, then it makes sense that the object should expand faster. So the expansion delta L here, here's my pointer. The expansion delta L should be proportional to the change in temperature. And the proportionality constant is this alpha, Greek symbol alpha, which is the coefficient of linear expansion. It's a property of the material that influences how much the material expands along one dimension. So the higher the alpha, the easier and the more expansion there is in one dimension. Right. Okay, so does this equation make sense? Okay, delta L, this is the expansion or how much the object expanded. It's proportional to how much the temperature changed. Of course, it should take into account the original length of the object, L0 initial length. So L0 will also be, you can call it as Li, L initial. And it should depend on this property of the material alpha, called the coefficient of linear expansion. If we translate this concept in three-dimensional, it will still be the same concept, but this time it's the expansion in volume. Okay, so expansion in volume, delta V, should then also be proportional to the change in temperature. It will also, of course, depend on the initial volume, V0. And the property of the material that influences how much the volume expands is this beta, Greek symbol beta, which is called the coefficient of volume expansion. So alpha and beta, they are properties of the material. You can look it up in the table or you can Google it. Coefficient of linear expansion of steel, for example. All right.
Beta equal to alpha Q?
Beta and alpha, not necessarily. Yeah, it depends on the object. So they can have, yeah, different values. All right, let's look at this example. 70-liter steel gas tank of a car is filled to the brim, meaning it's to the tip. It's almost overflowing, just a little bit more and it will overflow. It's filled with petrol at 20 degrees Celsius. And the car sits in the sun and heats up until both the tank and petrol are at 40 degrees Celsius. How much petrol will overflow from the tank? And we're given here the coefficients of volume expansions for steel. Steel, of course, for the gas tank and petrol here. All right, so have a little think while I write down what's given in the problem. All right, so we're given the initial volume of the gas tank, 70 liters, and the coefficient of thermal volume expansion of the gas tank. Since the tank is filled to the brim with petrol, then that gives us a clue that the initial volume of petrol should also be 70 liters, the same as the volume of the gas tank. And we're given the coefficient of volume expansion for petrol. So we know that the volume will change according to the change in volume should be proportional to the coefficient times the initial volume times the change in temperature. So we then have to get the change in temperature. So both the petrol and the tank went from 20 degrees Celsius to 40 degrees Celsius. So that will be a temperature change of 20 degrees Celsius. Okay. 20 degrees Celsius would, of course, be equal to 20 Kelvin, as we've seen in the earlier example. If you're getting change in temperature or temperature difference, Celsius scale is the same as Kelvin scale. I converted to Kelvin because the coefficients are given in the units of Kelvin to the -1. But again, if you did that convert your delta T to Kelvin, you can be forgiven because Celsius is equal to Kelvin when you're getting the temperature difference. But essentially, the approach here is to get the change in volume for the tank and get the change in volume of the petrol and see which of them, and see the difference in the change in volume, right? So we have everything we need to get the change in volume of the tank and the change in volume of the petrol. So let's do that. So the steel tank will increase in volume by this amount. Delta V is equal to initial volume 70 liters times the coefficient 3.6 times 10 to the -6 Kelvin to the -1 times the change in temperature 20 Kelvins. That will be a change of 0.050 liters. Do the same thing, the petrol will increase in volume by delta V is equal to the initial volume of the petrol times the coefficient of volume expansion of the petrol times the change in temperature. That will be a change of 1.330. liters. Right, so already you can see that the petrol will have increased more than the tank, but by how much? So then the volume of petrol that overflows will be the difference in this change in volume, because the petrol will have changed more than the tank. So that will be a change of 1.330 minus 0.05. 1.325 liters. So 1.325 liters of petrol will overflow from the tank if you fill your tank to the brim. Okay. So it's quite substantial. Actually, in my previous classes, I had a student who was also in the Air Force. And when we had this lesson, he said that in one morning, very early morning, that day they were scheduled to fly around the Pacific. So very early in the morning before dawn, they filled up the tanks of their jets, like to the brim. But there was some delay, and so midday came and they still didn't fly, and the petrol overflowed from the jet to the runway, and they had to, the fire department had to come to clean up the petrol that had spilled. So it's quite substantial. And you can also use this concept to sort of save money on petrol. So choose the time of day to fill your tank when your tank is expanded, or if you're running low on petrol, just park your car in the sun. The petrol will increase and the gauge will sort of increase in your tank as well. Did that a couple of times, it does work. So so the volume can increase quite substantially. We did try to calculate how much we would save by doing this trick and choosing the time of day. We can save like 2 cents in a week. So I don't know if that's worth it, but the volume does increase substantially. Right. Okay, any question about how we solve use this equation? The volume expansion. All right, I have a question. If you don't have a question, I have a question. How about if you have a hole, like a ring? The holes, when you heat up this ring, will the hole become smaller or will the hole become bigger? Depends where you heat it from. Well, to cease to believe, someone did have this question and they did do this. So I'll show you this video.
Okay, so I thought I would try.
That's not working. The sound's not working. So let's try this again.
Heating up again. Okay, so I thought
maybe I'll play it from here. Okay, it's not working. Okay, let's start this again. Oh, how come? You can hear the sound, but there's no video. Wait, let's. Okay, so hopefully this will work.
Wow. Look how much center the hole expanded by Gina and now going to
Are you convinced? Are you convinced? Did the hole increase or did the hole shrink? Just go back. You can try it yourself. Like, it's an easy enough experiment to try and prove it, but the holes do expand when you heat them, and regardless of whereabouts, which position you heat them, the hole does expand. So you can think of the hole as what happens there is you can think of the hole as being filled out by the same material, like it's not hollow. So when it expands all around. And in fact, the fact that the hole expands when it's heated is what's the concept used in shrink fitting. Like, have you seen these coins that consists of two different kinds of metals? So they start first with a ring. They heat this ring up. The ring expands, and then put in the filling, the middle part, and then they cool it down, and the ring contracts tightly around the center part, central metal. The same concept with fitting steel tires to the wheel. If you want something that's tightly fit, expand something and then cool it down to contract it, and it will fit tightly. Okay, so so holes expand. So let's look again at this example and see, how we apply the equation for the expansion. If you have a hole, so you have here an iron ring. Okay. It has an internal diameter of 6.420 centimeters at this temperature, initial temperature 20 degrees Celsius, and there's a rod with a bigger diameter. Right? Bigger diameter, 6.445 centimeters, also at the same temperature. We already know you need to expand the ring in order to fit the rod inside into the ring. But the question is, and it says here that the rod will only fit if there's an opening of 0.008 centimeters bigger than the diameter of the rod. The question is, to what temperature you should heat the ring in order to place the rod in it. So you have here the coefficient of linear expansion of iron. So only the iron's coefficient of expansion is relevant because it's only the ring that you want to expand, while the rod, which is made out of, it didn't say what the material of the rod is, but the rod is kept at the same temperature, 20 degrees Celsius. Right. So the approach here is that the hole of the ring must be increased from its initial diameter, 6.420 centimeters, to the diameter of the rod, 6.445 centimeters, plus the extra gap that will allow the rod to slip into the ring. And it's given 0.008 centimeters. So the diameter of the hole needs to expand from 6.420 centimeters to 6.453 centimeters. In other words, if we put this into given, what's given in here, the initial diameter should be 6.420 centimeters. Okay, the change in diameter, so the diameter should go from 6.42 centimeters to 6.53 centimeters. So that should be a change in diameter of 6.453 minus 6.420. Right? Okay, does that make sense? Okay, we had to find delta L, how much the diameter of the ring should change, because that's what comes into the relationship for the change in the length with the change in temperature. Okay. Right. Alpha, of course, is given 12 times 10 to the minus 6. Right? Okay. Good. Right, we have the change in length. We have alpha, the original length, L0, which is original diameter. We can then calculate what the change in temperature should be in order to have this change in length. Okay, so we do that. The change in temperature is equal to, okay, coming from, of course, alpha L0 delta T. Plug in everything from before, you get a change in temperature of 4 to 8 degrees Celsius. Okay. So what you have obtained from this equation here is the change in temperature. What the question is asking is, what temperature do you need to bring the ring to? Meaning, what should be the final, if the ring is at the initial temperature of 20 degrees Celsius, what should be its final temperature? What should be its final temperature? Delta T, of course, is final minus initial temperature. So therefore, you should bring your ring up to the temperature equal to its initial temperature plus how much the change in temperature should be in order to accomplish this change in length or diameter. So that will be 20 degrees Celsius plus 4 to 8 degrees Celsius, or 448. So if you heat up the ring to a temperature of 448 degrees Celsius, it will have a temperature difference of 4 to 8 degrees Celsius compared to its initial temperature, and a temperature difference of 4 to 8 degrees Celsius results to a change in diameter of 0.003 0.033 centimeters, which then results to diameter equal to 6.445 plus 0.008 centimeters. Right? Okay. Does the solution make sense? It took a little bit of working, but I hope it makes sense. And yeah, right. Okay, so far we've been talking about objects that expand, and they're free to expand, right? There's nothing holding them back to expand. But sometimes objects are fixed. For example, if you have a building and it has a beam, like the roof has a beam and it's fixed at both ends. What happens when you have a fixed object, an object fixed at both ends is what I mean, an object fixed at both ends, and you heat up this object, of course, this object will expand, but then there is an obstruction, or there's something preventing this object from expanding. So here's a picture of the scenario here. You have a beam, it's fixed at both ends. So you hear the object is heated up, right? So you have this red thing, red visual here, showing an increase in temperature. We learned that the beam will expand linearly. So you have this linear expansion. But the beam is fixed at both ends. So here it's fixed at both ends. So at the ends where it's fixed, there will of course be a force that will oppose the expansion of the beam, right? Okay, at these ends where it's fixed, the force from the fixture will oppose or obstruct the expansion of the beam as it's heated up. So as a result of that obstruction, and there's nowhere else for the expansion to go, the result is the deformation of the object, or deformation of the fixed beam, as you can see here. Okay, right? The beam still needs to expand because of the increase in temperature, but the opposing force provided by the obstruction at the end will cause the deformation of the fixed beam. And the force that's exerted by the fixed end is what we call thermal stress. So thermal stress, we've learned about stress and strain, stress being related to the force per unit area. Thermal stress is therefore the force exerted by the whatever's obstructing by the object obstructing the expansion per unit area of the expanding beam. So it's proportional to the change in temperature, because you only have thermal stress as a result of the increase in temperature and as a result of the expansion of the object. So thermal stress should also depend on the coefficient of linear expansion. As the temperature increases, the object expands according to its coefficient of thermal expansion, and the resulting deformation is a function of the elastic modulus of the material. So thermal stress will then be a function of all of these three. The linear expansion, how much the object expands as a result of the change in temperature, and the deformation is according to the elastic modulus of the material. So thermal stress is exactly what caused the railroad tracks in this picture here to deform and appear warped in this case. Right? Okay, so it is really, as you if structure, as you design structures and all of this, make sure you account for thermal expansion or thermal contraction. Otherwise, yeah. All right, so any questions about this topic? What we've learned is we've defined temperature, we've defined the SI unit Kelvin and how to convert between Celsius to Kelvin. We've seen how objects expand and we've calculated the amount of expansion according to their coefficients of expansion. Right. So today we've looked at solids. In the lecture tomorrow, we will look at how gases behave when the temperature changes. So we'll talk about what we call ideal gases. If there are no questions, I wish you a good day, and I'll see you in the lecture tomorrow.